So I guess we can start in order to progress. So, hi, my name is András Lukács and I'm working at the University of Pécs at the medical school at the Department of Biophysics. This means that my focus today will be a little bit of biological or biophysical at the end, because of course we can talk about ultra-fast processes in other fields as well, but I will focus on some applications what we can do in biophysics. So that's why I changed slightly my talk, and I changed that functional dynamics of proteins revealed by ultra-fast spectroscopy, because my research is focusing mainly on protein dynamics, and we are using a couple of different ultra-fast spectroscopical methods in order to reveal these protein dynamics. First of all, of course, we have to discuss a little bit or slightly what does it mean ultra-fast, because the meaning of ultra-fast was changing in the last couple of decades, because my mentors and professors, when they started in the field, that time ultra-fast was picosecond, and that was very interesting, and they did pioneering work, and it was exciting. Later, in the mid-90s, as the femtosecond lasers widespread all over the world, of course ultra-fast became femtosecond already, and as we are here in Szeged, where we have this ELI facility, or this is under construction at the moment, ultra-fast is going to be the second generation, but at the moment we are not dealing with at the second generation or at the second pulses, as we have maybe less biological implications, at least at the moment. So ultra-fast for me at the moment, it means femtosecond, from femtosecond to picosecond laser spectroscopy, and I'm in the field for more than, I don't know, maybe 10 years. So basically in the beginning I started to work in a laser company when we were manufacturing femtosecond lasers, and this was a small company, and later I left the country and I was working at École Technique in Paris, or in the suburbs of Paris, and where I was working with some very big names in the field, Jean-Louis Martin and Martin H. Voss, and who were using this ultra-fast spectroscopy in the field of protein dynamics. And later I moved to the UK, where I was working with Stephen Meach, and we were continuing this ultra-fast travel together in order to investigate some clinical proteins. So today, this is the outline. I'm going to talk about why do we need at all ultra-fast laser spectroscopy. So what is the reason? Why do we need ultra-fast time resolution in some biological problems? Because if you're from the biological field, you know very well that maybe the most interesting things are not happening on the femtosecond or picosecond time scale, but anyway, I will show you some implications or some reasons why it's good to use some ultra-fast laser spectroscopy. The next question, of course, what do we need for ultra-fast laser spectroscopy? Of course, 20 years ago it was a bigger question, because everybody had home-built systems, and you have to do a lot of job in order to have a good system. Nowadays, if you have enough money, you can buy it. So the question is now, it's less interesting. You can buy home-built, or you can buy complete systems, and just you pay the money and you will get everything. But I will show you some details, because I guess it's exciting that what do we need for laser spectroscopy. And I'm going to present a couple of laser spectroscopical methods we are using here as lifetime measurements, fluorescence lifetime measurements using optical immersion techniques, and also method we improved or we developed, and also visible and infrared absorption, what I'm working on almost all the time. So this is our outline today, and I guess for a good couple of of minutes I will talk about that why do we need definitely the ultrafast spectroscopy. Well, because there are interesting processes, of course, which take part on the femtosecond and picosecond time scales. And what are these processes? I will show you today two processes in details. And the reason that I'm showing these two processes because I'm working on those proteins. And one of them is the photoliase, which is a very interesting protein as it repairs the DNA lesions using visible light. And if you remember, maybe you remember that last time the Nobel Prize in Chemistry went for photoliase research. So that's an interesting field, I would say. And the other is another so-called flavor proteins. These are bluff domain proteins, which means blue light receptors using flavin. And I will show you that also we have some couple of processes which are functional, and they happen also on the femtosecond, picosecond time scale. So it's happening ultra fast. Okay, so just a short, small slide about why does it happen, or when does it happen ultra fast, or what would happen. So as you remember in the fluorescence, when we are talking about fluorescence, very exciting, the electrons from the first excited state, and they will relax, or the molecules, they will relax back in a certain time, and they will emit the fluorescent light, actually. So now what happens in this case, that sometimes this process is very, very fast, typically in cases when we have an electron donor, or it's called here electron-rich quencher. So we excite the molecule, and we have another molecule which can donate an electron. And what happens in that case, that it donates this electron from here, and it will fill this hole here, and basically the excited state goes away, and we will have two radicals for a while. And this is, and I will give you some examples that this process happens actually in the biology quite many times, and which is even more interesting that this process is functional. So it should happen in order to have the function, especially in photoliase. So this is why we need, if you want to catch this process, or we want to see this very short transient fluorescence, in this case we need ultra-fast spectroscopy, so we would need some ultra-fast time resolution in order to see these processes. So now let's talk about a little bit about photoliase. So maybe you have heard about it, the UV light can induce some damage in the DNA strand, and we have, or it's known, two major lesions in the DNA. So either the cyclobutane pyrimidine dimers are formed, or this photoproduct is formed. So, and that, of course, this is what happens here. And of course, this is bad, because sooner or later it will get, let's say, in humans, this means the skin cancer. That's the end of the story. Now, we know photoliase, which is a protein, which can repair in a very special way these DNA lesions. And the way how it works, it's very interesting. So we have this pyrimidine dimer here, and in photoliase, this protein, it has a cofactor which is called flavin, and the flavin is in a reduced form. What happens that the light excitation comes, we excite it with blue light, and the electron jumps to the pyrimidine dimer. And due to this reason, the dimer will split. Actually, it splits, and the electron is going backward, jumps back, and the photoliase is still in a reduced state. The main reason here, the main thing for the photo repair, that the FAD, I mean the flavin, should be in this FADH minus fully reduced form. Okay. Actually, we have another process in photoliase because the reason we know about this, because if we express photolysis and we purify the protein, the protein actually looks slightly bluish because the flavoring it's in the semi-reduced state. We have this FADH dot state. But and actually here just I showed a small scheme later maybe I will talk about that flavin can exist in a couple of different redox states and can switch back and forth between these states. So what happens here that if you shine some visible light on the photolysis, an electron transfer cascade happens and reduces basically the flavin. So it becomes a fully reduced state. This is also an electron transfer, and of course it happens very fast. And these are just small, these are the spectra of the different redox states of the flavin. Now, I'm just showing here the time steps of this process, and you can see that indeed this is ultra fast. So after excitation, everything happens rather in 30 picoseconds. So we have very fast steps, and actually in some other proteins, like in cryptochromes, which are homolog proteins of photolysis, these primary steps happens even on the femtosecond, couple of hundreds of femtosecond time scale. So it's indeed ultra fast. Now, this was one example that is biological, it's important. Now let's think about the flavin. The flavin it's interesting itself, because what we had in photolysis that's called FAD, this is the flavin adenine dinucleotide, which is the whole thing. It has the whole orbital chain included. And if we compare, and this has happened already a long time ago, if we compare the fluorescence lifetime of the flavin, I mean the FAD, and we compare to the fluorescence lifetime to the flavin mononucleotide, which is FMN, there will be a big difference. As you can see on this scale, that the FMN almost doesn't change, or not very fast in this time scale, and basically the decay of the FAD is much faster. And the question, why does it happen? Why is this big difference? And the thing was solved by Tom Visser, and the interesting thing here that we have this orbital chain, and basically this adenine ring can donate an electron to the flavin, to the isoalloxazine ring, and electron transfer happens, and this electron transfer basically quenches the excited state. So this is what I was talking about. So basically, if we measure the fluorescence lifetime of the flavin in solution, I mean FAD in solution, we are going in with normal, let's say, single photon counting method. What we will get is something 3-point-something nanosecond. That will be the lifetime, what we can see at that resolution. If we measure with our system I'm going to talk about, we will get a lifetime around 9 picoseconds or so. Because even in water, and of course if we are changing the pH, this will change. Even in water we have two different subpopulations. In what subpopulation is called a closed state, which is this one, and the other will be the open state when the orbital chain is far from the isoalloxazine ring. And in that case, in the open state, that will give you the 3 nanosecond fluorescent lifetime, and the closed state will give you this one, the 9 picosecond fluorescence lifetime, because due to the electron transfer, this will diminish the fluorescence lifetime. So basically, at pH 7, we can measure both of them. Okay. Now, if we think about actually, in general, we can say that if we excite a flavin, FAD or FMN, and it gets excited, if we have an electron donor around, it will accept, or it will pull out an electron from the neighborhood, basically. And actually, this we can see in many favorable proteins very easily, even though, of course, the process is not functional, so it doesn't need for the function of the protein, but we can observe it. So that was measured basically from Zhang and Ziwei. Ziwei got the Nobel Prize in 1999 for femtochemistry, and for Transient transient absorption. And basically what happens here, you excite, let's say the glucose oxidase, you can excite the flavin with normal blue light, and because we have tryptophan around, we have a couple of tryptophans here, we have a tryptophan, we have a tyrosine here, another tryptophan. So basically we have a lot of electron donor around, and an electron is pulled out from one of them, and the flavin will relax back to the ground state very, very fast. Basically what we measure here is something around 10 picosecond, what we see in general. This process can be even faster in a protein called flavodoxin. In flavodoxin we have FMN, and we excite FMN also with the blue light to pull out an electron from a tyrosine or a tryptophan from in the neighborhood, and it will relax back very, very fast. I have a picture of that one because we measured it a couple of years ago. Yes, we have here, sorry. So in GOX we have different of course we can stabilize the different redox states of the flavin, but let's talk about only the oxidized state, which is this case. In GOX relaxes back something like 10 picosecond. Here you can see that the relaxation is very, very fast in the flavodoxin. So basically it was at the limit of our time resolution that time. Okay. My other example is the family of bluff domain proteins. Bluff domain means that blue light sensing using FAT. And this is one of the most known member of the bluff domain proteins. And what happens here that this is a transcriptional factor, this PPSR, and this is our protein which is called APPA or APA. So basically what happens here that if we shine the light, and they form a complex in the beginning at low light level and a low oxygen level. What happens actually, if you shine light, blue light in it, the complex will dissociate, and this PPSR will basically block the photosystem biosynthesis. And our question was that if we have the bluff domain at the N terminal of the protein, and we have the domain which binds the PPSR C terminal, and so basically what leads to this release of the complex, or the release of the PPSR, and what is basically what happens here, that is the protein will absorb a photon, and this absorption will lead to larger scale movement of the protein. It's very interesting itself, why does it happen? And if you take a look at the absorption of the protein, what happens that if you shine a light on it for 2 minutes or even less, you will see the so-called that in the so-called light state, the protein will shift kind of 10 nanometers to the red. So originally, this is what we have, the dark state of the protein. If you shine light on it, it will shift 10 nanometers, and this is the so-called light state. If you take a look at the photocycle, what we can see that the protein will stay in this light state for almost half an hour, and later will go back to the original dark state. And this was 10 years ago, the first photocycle scheme, what they made, but we made it more precise recently. But I will show you some results on that one. So now, these two examples were, why do we need ultra-fast spectroscopy? We need ultra-fast spectroscopy because we have ultra-fast processes. So in order to investigate or follow the ultra-fast processes, of course, we need some kind of good time resolution. And this is what we have. Now, the question, of course, and there's a big question 10 years ago, what do we need for ultra-fast spectroscopy? Well, so we need at least ultra-fast laser oscillator, but it would be better to have an amplifier too. And so usually this was basically a huge development in the field when the titanium sapphire oscillators came on the field, kind of 15 years ago or almost 20 years ago, because they had a good repetition rate, and they have also good pulse energy, and these are used these times or today as well. So if you go and you want to do some 2-photon microscopy or fluorescence lifetime microscopy or something like that, you will need a good titanium sapphire oscillator. So this was a huge advantage or huge development in the field. Also in that time, kind of 20 years ago, they introduced the regen amplifiers, which is very good because we can have much higher pulses, so we can use that energy for many things. And I will show you those applications. And we need the time resolution, a good time resolution, and basically what happens here that our time resolution is limited by the pulse of the laser, as you will see. I will show you why. And the typical resolution nowadays of these good or even commercial systems, 100 or 200 femtoseconds, depends on the provider, the laser manufacturer. And but of course, there are some systems which have a better time resolution. They can be even better than 50 femtosecond. When I used that equal technique, that was roughly 50 femtosecond, even though we couldn't really use that high time resolution because our processes were slower than that one. Okay, I won't go in the very details of the mode locking, but we have to deal a little bit with it, because for the ultra-fast laser spectroscopy or for ultra-fast systems, we need mode lock lasers. And maybe you learned about mode locking or pulse laser in the last days, so you will, I don't know. Maybe yes, maybe not. But we have a couple of different ways how to achieve mode locking, and what I'm showing today it's a so-called CAD lens-based mode locking. But anyway, what you can imagine easily is if we have a laser, if we have a cavity, we have a couple of modes inside the laser. And in the case of the CW lasers, my pointer, we have these modes, and they are phases random, so they are not connected to each other, or they are not synchronized at all. If you have a technique, or if you have something, a way to synchronize these modes which you have inside the cavity, this will give you a very short or even ultra short pulse. So this is what happened. And actually, I won't go into details today because it takes a long time, but CAD lens-based mode locking was invented in that way that it initially introduced a little bit of perturbation in the system. And mode locking, this type of mode locking was invented that the screwdriver fell on the table, you had this small perturbation, the CAD lens-based mode locking started, and you had a ultra short pulse and was sustained inside the laser. So this is exactly as it happens. Unfortunately, it happens in the other way as well. If you are working in the lab and the screwdriver fell on the table, you can stop the mode locking as well. So time to time it happens that something falls on the table, and your mode locking is gone. Nowadays it's not so bad because Spitfire from spectrophysics or the coherent lasers or whatever, they are very, very good, and actually mode locking is easy. You just click the button and it works. But in good old times, you have to spend, let's say, half a day or 2 days, depends. Typically after a Christmas holiday, 2 days to get back the mode locking. Because what happens during a Christmas holiday? Well, heating is turned off because nobody is there. Let's economize on the heating. So if you're economizing on the heating, everything is cold. This means that all your mirrors and everything is bended, so you switch on the lasers, nothing happens, you wait half a day, nothing happens, and so you have to realign everything with the good old lasers. So this is what happens, or usually happens with the old systems I used to use. And so it needs some time. And it was a good challenge that time to get back the mode locking. But you're so happy after that you get back the mode locking that you feel, how can I say, paid back or repaid, that it was a good story and it was a good challenge. I'm really sorry for my students that they cannot fight with the mode locking for a couple of good days. But they are fighting other things, so it's okay. But that was a huge, how can I say, it's a good feeling when you have your lasers mode locking again and you can see all those processes what I'm going to show now. Okay, so the titanium sapphire laser, that was a huge development in the field, as I said already. It's a very good material, so you can pump it in a quite broad band. And initially we used to pump them with R9 lasers. Nowadays we have this neodymium YAG lasers with a 532 nanometer central wavelength. But it's a good wide range, so you can pump it with many things. The other thing that their thermal stability, thermal properties are very good of titanium sapphires, so you can pump them quite with a huge energy. Of course, you need some kind of cooling system, but anyway, your crystal won't crack easily and works very. It keeps the pumping very well, and it's tunable in a quite wide range. While the central laser here maybe it's 700 something, it works, in my experience, they work best at around 800, 780 nanometers usually, and but with these nice new lasers, let's say from spectral physics or coherent, you can easily tune your range with the electronics, and you can just click what kind of central wavelength you want. So this is also good property of TISF lasers. Now this is how they look like. It's very simple. So you are pumping your crystal with a green laser, CW laser. This is the pump laser, and of course this is your gain medium, your TISF crystal, and you have these two curved mirrors, and basically what you are maintaining in the cavity the laser pulses. This is, I'm not going to talk about this. This is how to make these prism pairs are used to make your pulses shorter. This is also, you can write books about how to make the pulses shorter. We have different techniques. The prisms are very good, but we also have curved mirrors, which are also very important and very good. That was high invention in the field. My former boss, Robert Spöch and Ferenc Krauss, invented it, and that was a huge invention in the field, naming two laser companies of that, so it was really a success story. Now if we take a look, how does it look like in the reality? This is the laser. This is a home-built laser I was using, laser oscillator I was using in Paris, an Echo technique, and I enlarged the picture here. This is the central picture, and enlarged what we can see. So your titanium sapphire crystal is held in this holder, and you have, as you can see, the water cooling, because you have to maintain the temperature of the crystal to have nice pulses, and you avoid thermal lensing. And these are the curved mirrors, and basically your the pumping came from this direction. And so this is how it looks like. And as I said, in order to start the pulse, the mode locking, you need a small perturbation. So this mirror actually, has a rubber here, and you can push it, and then you introduce the perturbation. Of course, you have to align it well in order to get a good mode locking from the beginning. Otherwise, you can push for a very long time in order to achieve the mode locking. It's Okay, let's continue. So these were the titanium sapphire oscillators. So oscillator is the beginning of the whole thing of the story, because with oscillator you can do a lot of job already. You can have, let's say, a conversion, or you can use it for two-photon microscopy. In that case, if you have two-photon excitation, basically you can excite those dyes which can be excited at 400 nanometer. So it's perfect. It can be used for many things. If you want to do something trickier, like transient absorption or infrared transient absorption, you need higher energies, and of course you have to find some ways how you can increase the energy. And I don't go in the very details of this amplifier systems, but in the beginning the surpass amplification was involved was discovered or developed by Gerard Mourou and his co-workers even in the 80s. And the idea actually is very simple. So what you have in the beginning is that you have a small pulse from an oscillator, and you are stretching out this small pulse and in order to have a picosecond pulse. Why is this? The idea or the reason for this is very, very simple. Because if you have a very, very high pulse and you amplify this short pulse, you amplify it, let's say, 1,000 times or even more, it will damage your optics. So what you do in the very beginning, you stretch out this pulse, usually with a grating. You have a pulse, a stretch pulse in time. It's a picosecond pulse. You amplify it somehow, and you are compressing back. I have some bad colors. And you are compressing back basically these parts again, but that pulse will be will have much higher energy. So this is how it works. And basically, this is our amplifier. It's a Spitfire, and what we have here, as we opened it, let me see. Yeah. So this is an older system. This was a Spitfire. It was a oscillator called Tsunami. In that case, they had an active mode locking, and the beam comes in this way here and goes, and this is the grating which will stretch out your pulse, and basically after that, with this mirror, it's steered in this direction, and this is the region cavity, so the regenerative amplifier cavity. There you have actually two buckle sets, and what happens basically that you are pumping your region amplifier. This is a green light. You're pumping with a nanosecond laser, let's say at 1 kilohertz repetition rate. So you are pumping a longer laser rod, this type set rod here. It's longer than your oscillator. And basically you are keeping the pulse inside the system until it amplifies. So if you make several rounds in the rod and depletes basically the excited state, and with the buckle cell, the half of the buckle cell, you couple out a huge and giant pulse, which is not giant if you compare what will happen here in Szeged and Eli. But for us, it's a giant pulse, and if you focus it down well, you can make some pretty serious holes on many things. It will produce some plasma generation easily if you focus it down. So it's a very good amplifier, I would say. And this is our system, and I will talk about this system slightly later. Now, so this is basically, these were the most basic things what you need in order to make some ultra-fast laser spectroscopy. So you need an oscillator, you need an amplifier, and you will need some frequency mixing, but I will talk about that. So these are the tools what we can use for ultra-fast spectroscopy. So let's start with the simplest thing, with some science, fluorescence of conversion. This was easy. So basically what you do here, that you have a crystal, and this crystal has some very good properties, non-linear optical properties, and what you can do that if you have two different beams, you can make with certain frequencies, with omega 1 and omega 2, you can have an omega 3 frequency. This is what you do in the case of frequency mixing. This is a very speaking in a very general way, because we have, of course, a couple of sub cases of this. The thing is that, of course, the energy will be conserved and the momentum will be conserved in this crystal. And this is what happens. This is a phase matching problem here. So we have to match the phases. So now, of course, this is, you don't have to understand or remember, whatever. It's basically a birefringent crystal and BBO. So now let's get to the most typical subcase of frequency mixing, which is second harmonic generation. And what happens here, that you have, let's say, two photons with the same, go in the same directions, and they will basically, their energy, so it will add up, and basically you will have a photon with the double energy and half of the wavelength. So basically what you can see here is kind of bluish, and this was done with the 800 nanometer laser. So basically this is what happens. It should be at a certain angle, and with the theory, this happens at 29.2 degrees. You can tune it a little bit, so this is the so-called phase matching angle, what you need for the second harmonic generation. This is important for the upconversion. And now, this is just the first proving rule, the first proof of the second harmonic generation from the past. Well, this is just a slide, you don't have to remember very much. With different type of frequency mixing, I'm going to talk about the optical parametric amplification slightly later, and maybe I will mention this one, the optical parametric oscillation. The idea is the same. We have different type of beams, and we are mixing them in a crystal. So the idea is always, you have two different beams, you have two different laser lines, and you have your non-linear crystal, and you are doing your frequency mixing on that crystal. So this is one important substate, which is called optical amplification or collinear. This is non-collinear optical amplification. This is what we are doing in our lab. We are using for this one two birefringent BBO crystals, and what happens here that the first crystal is used for the second harmonic generation, and we will have a blue beam. And if we introduce the blue beam without anything else in this crystal, we have these very bright rings, which are called superfluorescent rings, which is very nice. On the other side, we will have a sapphire crystal here, which will produce a so-called white light continuum. So you will have a second beam, which will be whitish, and you are mixing them in the second BBO. And what you will have, that parts of the white light from the white light generation, I will mention it later, will be amplified due to the blue beam at a certain angle. And here the orange was amplified. Okay, this is very good because sometimes your protein doesn't match your excitation. So not every protein can be excited by blue beam. So if you need an orange or red, whatever, you are using a non-collinear optical amplifier, and it works very well. And actually your paths can be very short, especially in the case of a null path, which is we are talking about at the moment. These paths can be very short, even 30 seconds or so. So this is very useful. This is a quite bad picture of an OPO we have in our lab. Doesn't matter, right? The idea is also frequency mixing. So back to the fluorescence upconversion. What do we have here? It's very easy. So we have also here two nonlinear crystals. One is for the second harmonic generation, and the other for the mixing. So what happens here? We have a titanium sapphire laser, of course, and actually the scheme is the scheme of the system we were using at UEA in Norwich. And so this is a coherent titanium sapphire laser, basically, and you are making the second harmonic generation, the first BBO crystal, And with a dichroic mirror, you are collecting basically the leftover from the red, because only a small part will be used for second harmonic generation. The leftover is collected by this dichroic mirror, so it's good. And the other side, actually, the other beam goes in this direction. Basically here, we use some churn mirrors in order to compress the beams, because the time resolution of this system is very good, very short. So what happens, you are steering the blue beam until the sample, and you're exciting your sample with this blue beam, and you will get some fluorescence. And you are gathering this fluorescence with this reflective objective, and you are focusing down the fluorescent light on the second BBO crystal. And now what happens, that this red beam is coming via delay stage, and actually we can shorten or we can enlarge the path of the red beam. And basically this serves, and the red beam serves here as a gating pass. So when the two passes arrive at the same time, actually you will have, when the pass arrives here, it will generate a new frequency, close to 360 nanometers or so. And basically what you can do here, that you can scan or you can change the delay stage here, and in that case you can cut out so you are mixing some photons from early times or later times from the fluorescent light and fluorescent light. And this is what you are measuring, with it you are counting the photons arriving, and of course you will see that at early times you have a lot of photon coming, and later you will have less and less, and you will have a kind of relaxation curve here. Now this is the sample holder, and just showing what we have, this is the sample, what we have in a small cell here, and we're exciting the sample. It's yellowish, as you can see here, and we are collecting the fluorescent light with this reflective objective. It's called Cassegrain objective, basically. And now, as you can see, this is what we measured in the case of FAD, and also a couple of love domain proteins. Actually, just what I want to show you, that indeed it's the fluorescent relaxation here is very, very fast. And these are some just numbers, how fast are they actually. Now, we have actually a little bit better method for transient fluorescence, actually, spectroscopy, which we call the Kerr-Gade method, or Kerr-Gade fluorescence spectroscopy. The idea, and actually this is a method we developed in Paris at École Polytechnique, and it was published 2 years ago in this series.